So what we're going to find out here is whether a photon can transfer all of its energy to a free electron, or if this is impossible according to the rules of physics. So the first thing we'd want to check in questions like this is energy conserved and is momentum conserved? These quantities do not change whatever reaction we're considering. So first of all, let's consider the energy before and after this occurs. So it's E for energy. So first of all, we can write the energy of our incoming photon as hc over lambda. Next, we want the rest mass of our electron. That can be given by mec squared. Okay, and what we want to set this equal to is essentially a photon with no energy is nothing at all, because a photon has no mass. So here, after the reaction, all we're considering is an electron that's going to be moving quickly. Okay, so what we'll do here is we're going to write the gamma factor, which is a relativistic correction, multiplied by the rest mass times c squared. So now we've done the conditions for conservation of energy, we can do the conditions for momentum. Okay, so we know that the momentum of a photon can be given by Planck's constant divided by the wavelength of light. And what we're going to set this equal to is, again, the gamma factor, because we're considering a relativistic case, which is what we need to be able to show the true reaction, is gamma multiplied by me and c. Oh, sorry, not c. In fact, that's going to be v. So that is the final velocity of the electron. Okay, and so what we want to do here is essentially, all of these constants are known. We can consider any wavelength of light, which is fairly arbitrary. The mass of the electron is fixed, speed of light is fixed. So what we could do is find out what the final velocity of the electron is and use this to tell us whether this reaction is possible or not. So what I'm going to do here is, you notice that we have h over lambda here, and we have h over lambda here. So what I'm just going to do is sub this gamma me times velocity. I'll put a subscript there for the velocity of the electron, and I'm just going to put that in place of the h gamma here. So that what that leaves us with is gamma me ve, and then we've got a c there. Okay, and we can just write the rest of our energy conservation equation in there. Okay, and now what we want to do is tidy up this equation a bit, because there's a lot of things we can cancel now. And the first thing we'd notice is the mass of an electron. Each term contains that, so we can divide through and remove it from the equation altogether. Okay, and that leaves us with some c's. So what we're going to do next is divide through by the speed of light. Okay, which simplifies it further. Okay, and finally we're going to divide through by gamma to make that a little simpler as well. So that leaves us with just the electron velocity, c divided by gamma here, and then just c here. So the next thing we're going to want to do is actually sub in for this gamma factor here. Okay, so this is a standard formula which tells us the relativistic correction when we're moving fast enough, although the effects are always going to be present. They're just going to be negligible unless you're approaching the speed of light. So it is always valid to use it, but it will only give useful results sometimes. Okay, so that's our gamma factor there. So what we can see is we've effectively got a 1 over gamma here. So we're just going to sub that in and that gets rid of that 1 over there, because 1 over is itself. Okay, so let's move this down here now, actually up there a bit as well. So we've now got the velocity of the electron plus c multiplied by 1 over the gamma factor, which is just this bottom bit here. And that's going to be equal to c. Again. So what I want to do next is get rid of this square root, because that's going to make it difficult to solve. And so I'm just going to move that velocity part over to that side. And so then we can square each side to get rid of this square root sign. Okay, so we've now got the speed of light minus VE. Okay, so what I want to do now is square it all. Okay, and you'll see why in a sec. So that gives us c squared there, and then we're just going to remove this square root here. Okay, so we should be squaring that c. Okay, and then this is equal to that squared. We can quickly expand this. So we get c squared. We also square that, which is plus v squared, and we're also multiplying c by v twice, because it's a quadratic, which is going to give us minus 2vec. Right, so let's expand this bit next. That gives us c squared minus, and we've got, now we're going to have c squared times v squared over c squared, which is just v squared. Okay, and over here we can write what we have out before, c squared plus v squared minus 2vc. Okay, we just need a little bit more room now. Well, actually, no, I can go up here. Okay, so now you can see there's going to be some things that cancel out now as well. We can take away c squared from both sides, so we'll do that, and we could also move this over to that side and that over to that side to get the v squared terms and the regular v terms on either side. And what that's going to leave us with here is v squared is equal to, 2v squared is equal to 2vc. And then we divide through by 2v, and we find that v must be equal to c. So this now is the condition on the electron, the condition on the electron's final velocity for the photon to completely disappear, basically, for it to have zero energy at the end of the reaction. And you can see that it requires the velocity of the electron to be equal to the speed of light, which is fundamentally unphysical. So, okay, so this shows us why a photon can never transfer all of its energy to a free electron, because it would require the electron to travel at the speed of light to do so.